features of an equation of state. Most complicated is when you have a temperature which is less than the critical temperature. So what we plotted, typically equation of state such as the van der Waals or modifications of it at a temperature less than the critical temperature would look like this. So we pointed out that we identified two important divisions where those are the pressures where the PV curve undergoes a maximum and a minimum. We call that PV and PA, right? So what we can identify roughly is this to be the liquid branch of the isotherm. This is the gas or vapor branch, and this is the unstable part which is to be discarded, because along that we can easily see that dP by dt is greater than 0. So that is, it gives an unphysical part. So what we pointed out was that when you have pressures less than PA, very easy to identify the state corresponds to the gas state. And similarly, when I have a pressure greater than PV, then also we have only one route to the cubic equation. That is easily identified as the liquid route. The complications come when I given a pressure between PA and PV. Let's say I take this pressure called P1, right? So now at this pressure there are three routes. The middle route we discard as being unphysical, and these two routes is tempting to interpret them as the liquid and vapor, right? This being the liquid. Remember, I made a mistake. I think I interchanged the meaning of these two in one of the diagrams yesterday, but clearly this is the liquid, this is the vapor. But however, the catch in that is that since there are an infinite number of pressures between PA and PV, and at all those pressures you can identify three routes. So discarding the middle route, we see have two routes. They cannot all be identified as liquid and vapor, because we know that at a given temperature there is only one pressure at which liquid and vapor exist in equilibrium. It's a well-known fact for pure substances. So we cannot have an equation of state that violates that. So key point here is first to recognize, because we've always been saying, whenever I have let us say a transition from one state T1 T1 to another state T2 T2, I didn't really mark them on the phase diagram, but I sort of said that you have to assume that there is no phase change when we go through the integrals, calculating the property changes. We assume that there is no phase change taking place between these two states. But we never really had a means of verifying until we were able to plot these states on the phase diagram. You cannot really check whether in fact they are in the same phase or not. Right? So you should very clearly understand phase diagram of a pure substance, either on the temperature pressure diagram, so there is no information on the volume, or on isotherms like these. Right? So the first step, since we have a problem, for instance, let's say I give a change of state P1, let's say I call this P1. Right? So I said the particular body of fluid is in a state corresponding to this point. That means temperature is the same T1 for all points. So the state is P1 T1, right? Now let us say that the second state, I will say, is also at T1, and I give you a pressure P2 which is greater than PV. So clearly we know that between these two pressures there is a change of phase happening. One is on the gas side and another is on the liquid. So what it means is that now when we integrate from the ideal gas state, when we are considering the departure function, it has to stop at the gas phase, but I don't know where the gas phase stops, where the liquid phase ends. If I am given two states here on the gas part itself, then there is no problem in integrating. Similarly, also we don't need the departure function here. I can give two states on the liquid branch very clearly. Then there is no problem. But if I give a state, a change of state, which has in between this region, which I have not clearly resolved, then there is a confusion as to how far I can integrate on this, and then how far I have to integrate on the liquid, from where I have to start on the liquid, and how to also account for the transition. For instance, if I ask you to calculate the enthalpy change, H of P2 T1 minus H of T1 T1, right? So first I have to, unless I identify what the Psat is, I have no way of even carrying out any kind of calculation. Once I have to first identify Psat, then I will integrate from P1 to Psat on the gas phase. Then I have to add the transition, the change from the vapor to the liquid, and then I have to integrate on the liquid part. So first step towards any such problem is to identify what the saturation pressure is. So any pressure, P2 may not be here, but P2, let's say, is between PA and PB. So I don't know, unless I have identified the saturation pressure, again I have no clue. I mean, in the, P2 is, I'm talking about this P2, let's say, is given to be this between PA and PB. Again, I don't know whether we are in the liquid state or in the vapor state, or we are going to have to encounter a transition or whatever, right? So suppose now let us assume that I have found out what the saturation pressure is. Saturation pressure clearly has to lie between PA and PB. So that is the only range over which you have two routes. You discarding the middle, right? So let's call this PA. So let's now say I somehow am able to find the saturation pressure. I give you the saturation pressure as determined from the equation of state. Let's say I give you that. You have to carry out the calculation. I will tell you how to do that. So this is given to me to be the saturation pressure. Now, what can you say about the states between PA and PB? Suppose now let us say I give you a pressure, call it P, let's say 1. Now this also has 3 roots, right? This I am going to this I am going to cross because this is on the unstable part. Now there are 2 roots. Which root will you select, or which is the relevant root? Or both? Both roots I have to consider as physically meaningful. Which root represents the actual physical state of the fluid? The root on the right side or the root on the left? On the right side, because now I am below the saturation pressure, so phase transition hasn't taken place. So that is the key point. Once I determine what the saturation pressure is, now it becomes clear which state is what. The problem doesn't exist for pressures below PA. It never existed. It's very clear. That is the gas state. But there is a problem between PA and PB because I find 2 roots discarding the middle root, and I don't know which is actually where. I have to take both, or is only one value. Now that I have told you what the saturation pressure is, so below the saturation pressure, even in the region where I have 3 roots, I have to take only the highest root, and that corresponds to the gas route, right? So let me see where I have the different colors. So what I have to now do is mark it with a darker. So this now becomes the equation, the isotherm. This is how it will. We have to simply discard not only the unstable part, but also these two parts. So this is what is now the reconstructed isotherm representing the phase behavior. So this is the crucial quantity. What it means is that below P equal to, so let's say now we can fully, so now we can clearly identify the regions. P less than PA, right? Only one route exists, and that will correspond to the PA. This I also discard. And this is on the transition between, so also on the unstable part. It's on the interface, so that I won't consider. So up to PA, no doubt at all, I'll choose only there's only one route really. I ignore this second route that is coming here. I'll continue to choose B on the gas part. Now between PA less than P less than P sand, of three routes exist, right? And three routes are given by the solution of the equation state, right? Discard lowest and middle route and choose the highest route, which is again gas. To discard means I am choosing only the highest route and P equal to P sat. What would you consider? Three routes are there again. Discard middle route. And what can you say about the other two routes? The vapor and liquid. So the lowest route corresponds to saturated. That's why we call it saturated liquid and saturated vapor. Right? Saturated liquid and saturated vapor. So lowest. So this is two-phase coexistence. Liquid vapor coexistence. This is probably the most important state in the whole of the diagram. Lowest is liquid. Lowest route I am saying corresponds to the specific volume of the liquid. Highest to that of saturated vapor, right? I can say S liquid, saturated liquid. The highest group corresponds to saturated vapor. Now, for pressures, now between again three routes. Discard middle route that's always there. And what? Which other route I have to discard? Between PB and PSAT. Middle route and the highest route. I have to discard. Right? And the lowest route is what I take corresponds to liquid, simply liquid. You sometimes refer to as sub-cooled liquid. Maybe subsaturated, you can say. Because cool, everything is at same temperature. what we call the subcooled liquid only. I don't know, I'll check the terminology, but it's not saturated liquid, it's because here we are considering everything at a fixed temperature, right? So we are looking at pressures higher than the saturation pressure, it will remain a liquid, right? So I should take only the lowest root, even though I have 3 roots, I have to ignore the higher root also, the highest root also. It doesn't correspond to vapor because there doesn't exist any vapor. Right? Yes? Yeah. So then P greater than or equal to Pb. So again I discard this too, because see, once you are on this plan, suddenly I don't come on to the Pb, so that really doesn't have any significance again. So ignore that point and group it along with the rest of the pressures, even though there are 2 pressures actually, 1, 2, and so that corresponds again to liquid, subcooled or whatever, or subsaturated water, right? So this is the identification of the states. So the moment you are given a temperature, an isotherm, right? So you want to fix the state. Suppose you are given temperature and pressure, right? So you want to fix the state. So we need to clearly identify what is the saturation pressure. Identify what is the saturation pressure. Then only you can clearly say unambiguously whether in the liquid state or it's a coexistence or it is a gaseous state. Right? So that is what you have to keep in mind. Right? So now suppose let's take the same, let's say now I want you to calculate basically the enthalpy change delta H between this state, and for convenience I can also move to another temperature. Right? We now do that. How this isotherm will look like as we go to higher and higher temperatures, what will happen, right? And we'll finally reach the critical point and see the significance of the critical point. Right? So suppose let's say this is my P2, this is my state 2, and it is at P2, and this is at T1. Right? So what I will do is, I want to calculate delta H, right? So H of P2 T1 minus H of T1 T1 is first, I will put this as H of P2 T2 minus, I have to come from that side. Okay, I'm coming from here. Right? It is P2 T1 minus H of sat of T1 T1. Everything is at same temperature. So this is the first step towards handling change of phase. You will see that if I go to another, the second state is at some other temperature and some other pressure, then I have different choices of paths, right? We will see how to handle that. But this I am just giving you an example within the isotherm itself, how much more complicated it is if you have a change of phase. So I will split it into 3 parts, right? Plus, so this really, I am integrating only from here. This is clearly HL. So I am integrating from the subcooled state to the saturated liquid state. I cannot integrate directly all along because you see that there is a discontinuity. Even though I have the equation of state here, this is the reconstructed equation of state. There is a discontinuity here. Right? So I have to handle that. So the integration can only be along the smooth portions of the isotherm. Which is why we said originally that when you're calculating all this and writing dH by dP, dH by dE and all this, you have to make sure that there is no change of phase in between. So we can integrate, yeah, please, continuously along a smooth portion of the isotherm or whatever. So minus HL, right, and then plus HL minus HP plus HL minus HP that I have to account for. You might not notice because it's the same temperature and pressure. Because all along we have considered the most general case, right, where enthalpy or internal energy or whatever, it changes between two states whose pressure as well as temperature are different, and we understand that there will be a change in enthalpy because the states are different. Here I have two states, the liquid, the saturated liquid and the saturated vapor, which are both at the same temperature and pressure. You might argue that that's why the dH by dt, dH by dP doesn't work here, because you might think that there's nothing changing. Neither the pressure nor the temperature are changing, so the enthalpy change should be zero. That's not the case. That way phase transition has to be handled separately. So we have to calculate that. We have as yet no means of calculating that. So we've all along considered only changes of state which are along the smooth portions of the isotherm, or more generally, even if you go out of the isotherm, smooth portions of the surface, right? Equilibrium surface. Then I have HP minus, right, H of P1, P1. This is in the gas phase entirely, gas phase branch. So this I can now write as H of HP. So this is along this. So I can write this as an integral. This will be along this branch. That would be dH by dP along this branch. If I want to write it in terms of integrals, I can write this as the first term would look like integral dH by dP, and I now put L to indicate that I'm integrating along the liquid branch of the isotherm. dP, the pressure is from Psat of P1 to P2, P2, P1, dP, plus HL minus HP, plus integral, right, P1 to Psat of P1, dH by dP. So we know that dH by dP that we have calculated earlier will now come into play. We are not directly employing the departure function here. Departure function is sort of an artificial construct. We don't have to be constrained to using it. It's convenient to have those formulae. But here we see that I can directly apply the coefficient without having to worry about the departure function. But I can also go to the because this doesn't involve a change in temperature, so I can directly do this. We also have things that depend on temperature, then we might have to use the departure function. So this I will put as G P1 dP. So here these coefficients, given an equation state, you can find dH by dP, you calculate those integrals, right? But how to calculate the, so now we have two problems. We know how to handle changes of state where there is no change of phase, right? Either you are completely in the liquid or completely in the gas phase. And but you can even handle if you are completely in the solid phase. It's even easier to handle because many properties can be assumed to be constant, even for the liquid phase. Pressure dependencies and all that will be quite small. But now have a separate set of quantities which are associated with phase change. We have as yet no means of computing them because all the quantities that we have constructed changes are within a single phase. So the first quantity associated with phase, the most important, is this. I don't know how to calculate that, so I have to take this up. This also, so how do you calculate EL minus EB or SL minus SB. All those we have to now introduce. But before we do anything, we have to find out the saturation pressure, right? So we'll come to that in a moment. But let's now look at how the equation of state would look like at higher temperatures. So what will happen, as I pointed out yesterday, as we go to higher and higher temperatures, the difference in the liquid and vapor properties, that includes all properties, the saturated, specific volume, specific enthalpy, and all those properties which undergo changes will become smaller and smaller. Typically, the way it is given is, for instance, if I will erase everything else, usually this is represented, the locus of the liquid state is represented by a curve which looks something like this. That means the next temperature, let's say I consider a temperature T2 higher than T1, right? It might look like this. So let's say this is the locus of all saturated liquid states, right? So the liquid state here will become like this. So if this is T1, DL of E1, this will be DL of E2. So that is now becoming higher. As you go to higher temperature, liquid specific volume is increasing. Correspondingly, the vapor now has to move closer to that. So this also will be along a certain locus. This is, let's say, the locus of all vapor states, right? So you have a dome-like thing, right? So that means at that pressure, this is the saturation pressure, Psat of T2, that will be higher than Psat of T1. The vapor volume will be, so this is VB of T1, this will be VB of T2. Right? This is how it will happen. And then finally, when the two meet, we have what is called as a critical isotherm. It will look like this, and we have an inflection point at the critical point. So the point where the vapor and liquid properties are meeting and finally they collapse into one, that's the critical point, right? So at the critical point, we can argue that dP by dt at the critical point will be equal to d squared, because the point of inflection is equal to 0. So that is a very important point from a practical perspective, and we'll now see why it is so. Right? So let's now take an equation of state, right, and apply this. So the simplest is the van der Waals equation of state. So I will take the van der Waals equation of state and see what happens at the critical point. Let's take dP by dP. This is going to be minus RT by d minus p whole square by dP only. There is no derivative to temperature. This will be plus 2a by dq. This is equal to 0 at the critical point. So this is at the critical point it is 0. So you have to see, basically what is happening is that you have, if you look at any other isotherm other than the critical isotherm, we see that here dP by dt is 0. 2 points will be there where dP by dP is 0. One is where the pressure undergoes a minimum. The other is pressure undergoes a maximum. You can argue why it should lead to an inflection point. It's difficult maybe to prove mathematically, but intuitively you can see that dp by dt is 0 here. Now, what can you say about d squared t by dp squared? It's certainly not 0 because it's a minimum. What will it be? It will be greater than 0, right? Here, d squared t by dp squared will be less than 0. Right? So now, what can you say about some point? Suppose I have a d squared t by dp squared greater than 0, and then it's a smooth continuous curve, and it becomes less than 0 here. So what can you say will happen to d squared t by dp squared somewhere in between? It will become 0. So clearly you can see that there is some point along this, the dp by dp is actually greater than 0, but d squared t by dp squared becomes equal to 0 somewhere. I can argue by continuity. Right? Here it is positive, and here it is negative, so it has to vanish somewhere. As you go to higher and higher temperatures, this whole region, it will now look, might be difficult to draw here properly. The whole region will shrink. This whole unstable region will shrink because everything is moving together. Actually, the 3 points are moving together. The point where dp by dv is 0, 2 points, and the point where d squared p by dv square is 0. The 3 points are moving closer and closer together. The limit of the critical point where you have no longer the unstable portion at all, everything has collapsed into one point. So we retain the dp by dv equal to 0 there, and also d squared p by dv squared. So I can give an intuitive explanation for why at the critical point we should have a point of inflection, because all these 3 significant points are collapsing into one point and retaining their character. Right? So dp by dv as well as d squared p by dv squared vanishes at the critical point, and all through this region is going to become smaller and smaller. So here it may become like this. So the region over which the domain over which d squared p by dp squared vanishes is also decreasing, right? And the difference in the pressures between dp by dp equal to 0, the PA and PP is also decreasing. So everything is moving together. At the critical point, they will collapse into one point, which will be the inflection point criterion. D squared p by dp squared is equal to, I have to differentiate this. I have to differentiate this once. So this would be 2r, and then I have to substitute. So I am differentiating and then substituting again for DC and BC. So I have this. Now I can simplify this and write this. Divide one by the other, right? Let's say I divide this by, or rather this by this, then I'll get RBC will cancel, right? So I'll get BC minus B, the whole cube, by BC minus B squared. So I'll get BC minus B. There will be 2 in the denominator is equal to 2A by 6A. So that will give me 1/3, and then BC power 4 by BC will give me BC. So what do I get out of this is that 3BC minus B is equal to 2BC minus 3B, which implies that BC equal to 3 times B. It's a very important result. So the van der Waals critical volume 3 times the parameter B, which also has the same units as the volume, as you can see here. Now I take this. Now I have already used one of these. Basically I am solving for BC from these two. The two equations in BC and DC. So I have it quite easy to solve because I am having non-linear equations, each one by itself. When I divide, I get a linear factor out. And so I get the value of BC. So I can substitute this BC into 3 in any one of those and I get a value for DC. That's also very well known, but I don't expect you to remember that. That can be written as now what about PC? How will you find PC? Here, so I have another equation here. This is also satisfied. The equation state has to be satisfied at the critical point. Right? So PC, suppose I take, now it has both PC and PC. So I substitute this and this into this, then I get PC is equal to A by 27 B square. So we can verify this. These results are very well known. What is the point of this? The point of this is that given a van der Waals fluid, it's a model fluid. So far we have not established any connection with the actual substance. Does it represent an actual substance? Okay. So you have a van der Waals fluid and you have an infinite number of van der Waals fluids. All possible combinations of A and B you can consider. What this says is that the critical volume, the critical pressure, the critical temperature are given in terms of the parameters A and B by this. So if I have chosen a particular value of A and B, I immediately know what EC is. If I give you a value of A and B, I can find out EC. So if a good way of checking is actually plot the isotherm at that temperature and you have to recover the inflection point. Right? In fact, above the critical temperature, the isotherms will start looking more and more like ideal gas isotherms. There won't be any big changes happening. It's all monotonic. Right? That's how it will be. That's a supercritical state. Now, however, these formula have to be inverted for them to be of use practically. Because what I want is I have a substance such as, let's say, methane. I want to represent it as a van der Waals fluid. So then I have to ask what parameters you will assign for methane. Now I'm talking about a particular physical, real substance. Right? Now this formula, when they are inverted, right, to express A and B in terms of PC, PC and BC, they give a means of assigning parameters for a particular substance because the critical properties of many pure substances are very well documented. Right? Because when I say I have a model equation of state, I want to represent an actual substance, you have to assign the parameters and they cannot be done arbitrarily. There has to be a certain rationale. The rationale is the critical constants are used to assign the parameters. Now for the van der Waals equation of state, there are only two parameters, A and B. So I need only two of the critical constants to evaluate A and B. So they can be either PC or BC or so typically PC is chosen because the volume probably density measurements are always subject to more error compared to the temperature and pressure measurements. So probably there's a lesser uncertainty associated with the critical temperature and critical pressure. If you look at further Smith and Banner's and Waals, they've given the critical constant to many substances. You can go and check how they look like, what are the units and so on. Right? So we want to express A and B in terms of PC and PC rather than BC and BC PC or PC and PC. Because otherwise, B equal to I can write PC by 3. That's quite convenient. But however, we won't choose that. We will write A and B in terms of DC and PC. They can be easily obtained from these two equations, right? Because if I divide again one by the other, I get B. Because A is appearing. So let's just do that. PC by PC is equal to A by 27 RB times 27B square by A. 27 will get cancelled. A is also getting cancelled. So we get B is equal to 1 over A RPC by PC. So given the critical temperature, critical pressure of a substance, so I want to model it as a van der Waals fluid. That's the equation I will use to determine the parameter B. B clearly will have units of the specific volume. We'll see later on what the units are. Now what about A? A I can write this as 27 BC times B square. So B square would be 64 R PC whole square by PC square, which is 27 by 64 R PC the whole square divided by PC. Right? So I've got A and B in terms of PC and PC. So given critical constants, we can determine the parameters A and B. So these are the parameters. So given any equation of state, your first job should be to find the parameters of the equation of state in terms of PC, PC, or if it has 3 parameters sometimes, it might also require the third constant. Now that is related, that's an important point. But here I am only using a part of the information, either DC and PC or DC and PC or PC and PC. Now you can also see that if I now take the product PC by RPC, the PC I have A by 27B square, PC is 3B divided by R, or rather RPC is 8A by 27B. So what do I get? Get 3 over 8. Now this is an important property, there is an important limitation of van der Waals equation. There are many equations which are similar to the van der Waals equation state. So what this says is, now I define a new quantity called the compressibility factor, which is defined as PV by RT. Now the compressibility factor is 1. It is not to be confused with the compressibility we have introduced earlier, isotherm or etc. Compressibility factor, right? So PV by RT is clearly 1 for the ideal gas, right? We pointed out one measure of the deviation from ideal gas behavior is the fugacity, right? This is another measure, PV by RT fugacity. If it is equal to 1, it's ideal gas. Further away from the ideal gas, the farthest this will be from 1. Here what we are having is that the critical compressibility of the van der Waals fluid is actually independent of the parameters A and B. Means all van der Waals fluid have the same critical compressibility, and that is 3 over 8, which is actually really 0.375. Now if we look at the critical compressibility of many of the substances, they lie in the range 0.22 to 31. That's what the books say. So clearly the van der Waals fluid is not expected to give very good quantitative accuracy to any of the properties, including pressure, volume calculation, or for that matter even saturation pressure and so on, because it clearly doesn't represent actual substance. Now, this is a limitation, because once I have chosen, this also shows that if I have chosen TC and PC to determine A and B for any given substance, then clearly its BC is not going to be predicted properly by the van der Waals equation of state, because the van der Waals says that critical compressibility has to be 0.375 for all substances, whereas it is not the case. Quite different from 0.375 for most substances. So this is an important limitation of van der Waals equation of state, and the fact that it has two parameters and only two of the constants can be determined is also related to this. Fact is that the critical compressibility factor is fixed once and all for all van der Waals fluids, and we have no room to adjust the critical compressibility of the van der Waals fluid with that of the actual substance. If we could do that, then it will certainly give a better agreement with the predictions of properties in the actual substance. We will take this up in tomorrow's class as well as a quiz